Hello everyone, in this video we are just going to interface variable resistor with the inbuilt ADC module available in the microcontroller TM4C123 GH6PM Texas TIVA series microcontroller. Let's get started. So now for the beginning, let us try to discuss about the various topics that we are going to cover in this video so that you can follow this video in a series. The first thing that we are going to cover is we are just going to learn about the working functionality of variable resistor or potentiometer, and then we will see the configuration of ADC module of TIVA C series microcontroller for reading the ADC step value, and then we will be programming, that is writing our logic for reading step value from variable resistor. And the fourth thing that we are going to discuss is we are just going to build the circuit in a breadboard for visualizing the output in the hardware. And the fifth point that we are going to learn is we are just going to visualize the output in the hardware. So these are all the things that we are going to learn in this video. So stay tuned till the last minute of the video. So you will be learning tons of things in this video regarding the ADC of the microcontroller and also regarding the working functionality of variable resistors, various applications of variable resistors, etc. So let's get started. So now let us move to the first point in our agenda, that is we are just going to learn the working principle of variable resistor for understanding the basic principles of variable resistor and various applications of variable resistors, how we can interface this variable resistor to the microcontroller, and also what are the ways of fetching the voltage signals from variable resistor. So for understanding the working principle of variable resistor, I have built a Proteus simulation circuit right over here. So with this circuit, we are just going to learn the working principle of variable resistor. So basically, variable resistors are nothing but simple resistors whose resistance value can be varied by rotating the knob available in the variable resistor, either in clockwise or in anti-clockwise direction. So this is a basic circuit with the help of which you can receive voltage signals from variable resistor. That is, usually variable resistors will be having three terminals. One on the left, second on the right, and third one is available in the middle terminal. To the left terminal, I have connected ground of the circuit, and to the rightmost terminal, I have connected the positive 5 volt signal. And to the middle terminal, which is the sensing point for the microcontroller, I have connected a voltmeter. So usually here in the middle terminal of the variable resistor, we will be connecting the analog pin of the microcontroller, using which we will be sensing and measuring the voltage signal as an analog source. So this is the sensing point, that is the middle terminal of variable resistor, and for now I have connected a voltmeter for testing the voltage signal, that is DC voltmeter. Now when I turn on the simulation, you can see my voltmeter is showing the reading 0 volt, since the potentiometer knob is available in the 0%, that is towards the extreme left side direction. And now when I try to rotate the knob of the potentiometer towards the other end, you can see there is variation in voltage signal. And when I place the knob of the potentiometer or variable resistor in the other extreme end, that is towards the right side, you can see I am getting a 5 volt signal in this voltmeter. That is nothing but the voltage signal provided right over here. So this is the concept. The resistance of the variable resistor varies based on the knob rotation of the potentiometer or variable resistor, and based on the resistance value I will be getting the voltage signal in the middle terminal. So when I place the knob in the 0%, that is towards the extreme ground end, I will be getting a 0 volt signal, and when I place the knob in the extreme right end, that is towards the 5 volt signal, I will be getting a 5 volt in the middle terminal, and when I place the knob in the 50% of the potentiometer value, I will be getting 50% of the voltage signal provided over here. That is, I have provided a 5 volt signal right over here. That is why I am getting a 2.5 volt signal right over here. And when I place the knob in the 10% of the potentiometer value, I will be getting 10% of the 5 volt, that is nothing but 0.5 volt. Similarly, when I place the knob in the 80% of the potentiometer, I will be getting 4 volt signal, which is 80% of 5 volt signal. So based on the knob rotation of the variable resistor, we will be getting a varying voltage signal in the middle terminal of variable resistor. So using the ADC peripheral of any microcontroller, you can read this voltage signal coming from variable resistor. And these kinds of variable resistors are most widely useful in applications like volume control, speed control, etc. So for now, I hope you understood the working principle of variable resistor. Based on the knob rotation of the variable resistor, we will be getting voltage signals in the middle terminal of the variable resistor. And now let's move on to the next part of the video. So now I hope you understood the working principle of variable resistors. So variable resistors are simplest form of analog sensors, which is useful for checking whether the ADC module in your microcontroller is working properly, or you can also use these kinds of variable resistors for applications such as volume control and also brightness controls of LEDs. So we are just going to fetch the voltage signal from the variable resistors, and we are going to read that voltage signal that is coming from the variable resistors, which will be in the range of 0 to 3.3 volt signal, and we will be visualizing the step value in our microcontroller. So this will be the range of step value for the voltage between 0 to 3.3 volt. So for the voltage range of 0 to 3.3 volt signal, we will be visualizing the step values in our microcontroller ADC module. So this is the thing that we are going to do. And in addition to that, we will be adding a particular LED for turning on and turning off the LED if the step value goes beyond a particular 50%. So that we will do later. And now let me just open the data sheet of the microcontroller TM4C123 GH6PM, that is TIVA C series microcontroller, for understanding the ADC module available in that microcontroller. So this is the datasheet of the microcontroller, and our microcontroller is having a inbuilt ADC module. So in the last video of ADC module working explained in a microcontroller, we learned that the ADC module uses successive approximation technique for fetching and converting the analog signals into digital format. So now I hope you will be understanding in a better way how we can implement that ADC module for reading the particular step value by passing a particular voltage level on the ADC channel of the microcontroller. So here you can see we are having an analog to digital converter, that is ADC, internally available in this microcontroller. So from the first page, you can visualize that an analog to digital converter is a peripheral that converts continuous analog voltage into discrete digital numbers. So as we discussed the SAC, that is successive approximation technique, in the previous video, so it uses the same technique for converting the analog voltage signals into discrete digital number. And this ADC module is a 12-bit resolution ADC. So as we discussed, there will be a particular resolution for the ADC available in a microcontroller. So our microcontroller, that is this one, is having 12-bit resolution ADC. That means the step value that we are reading will be between 0 to 2 to the power 12, that is 4095. So it will be actually 4096, 2 to the power 12 is 4096, but the value will be ranging from 0. So as it is starting from 0, we will be having total of 4096 numbers, that is 0 to 4095. So this will be my maximum step value for the voltage of 3.3 volt, and this will be my minimum step value for the voltage of 0 volt in a particular ADC channel. So that is why it is having a 12-bit resolution, and it is having 12 input channels. You can clearly see I am having 12 different ADC channels from which I can read 12 different voltage levels. So at a time I can read 12 different ADC values in my microcontroller, and each values will be ranging from 0 to 2 to the power 12, since the resolution of the ADC is 12-bit. And the major ADC in this microcontroller is divided into two different ADCs, that is ADC 0 and ADC 1, and these two ADCs will be having, and we are having ADC 0 and ADC 1, and these two ADCs will be having 12 different channels. As I mentioned, they are having analog input 0, which is connected to PE3 of the microcontroller, and analog input 1, which is nothing but the PE2 of the microcontroller. Analog input 2 is PE1, analog input 3 is PE0, analog input 4 is PD3, analog input 5 is PD2, analog input 6 is PD1, and analog input 7 is PD0, analog input 8 is PE5, analog input 9 is PE4, analog input 10 is PB4, and analog input 11 is PB5. So these are all the 12 different channels available in the ADC. You can use either of the ADCs, that is any one of these two ADCs, that is ADC 0 or ADC 1, for reading from these 12 channels. But physically available channels are these channels starting from AAN0, that is analog input 0 to analog input 11. And we are just going to read from only one channel. So let's take this first channel AAN0 to be PE3. So the channel that I am going to read the variable resistor voltage value is AIN0, that is PE3. And the other data that we require from this data sheet is the steps that we want to implement for configuring the ADC module, and also for reading from the ADC module, reading the step value from the ADC module. So let me just scroll down a little bit. So I am not discussing everything available in this microcontroller dataset. I am just discussing the things that you require for interfacing or for configuring the ADC module. So if any new requirement is required for you, just ping me or write on to smtrainingacademy@gmail.com, so that I can try to help you in such situations. So let me just open the module initialization page. So here you can see these are all the steps that is involved for initializing the particular Gpio pin as ADC channel. That is, we will be following these steps for configuring a particular Gpio pin as ADC channel, and in addition to that we will be following these steps for configuring the sample sequencer for reading a particular ADC value from the ADC channel. So these two are the configurations that we want to do before going to the actual reading part of ADC. So let me just write down all these configurations step by step, so that I can implement it in my KEIL Microvision IDE or in my programming part. So first thing is, I just want to configuration of Gpio. as ADC channel. And the second thing is configuration of sample sequencer for ADC channel. So these two are the configurations that we want to do, and then after the configuration we will be moving on to the actual programming part of reading the ADC value from the ADC channel PE3, and the channel that I am going to use is PE3 and the ADC module that I am going to use is ADC0. So I will be neglecting this ADC1. I will be using the ADC0 right over here for reading the ADC channel, ADC value. So now let us try to write down the steps that is required for configuring a particular Gpio as ADC channel. So first thing is I just want to enable the ADC clock using Rcgc Gpio. So let me just copy all these things. Let me just copy these things first. So these are all the 5 steps that needs to be implemented for configuring a particular Gpio pin as ADC channel, and these are all the steps that needs to be implemented for configuring the sample sequencer in our ADC module, for our ADC module. Now let's start writing the programming in our KEIL Microvision IDE for fetching the step value and turning on a particular LED when the step value reaches more than 50% of the step value, that is 2048, and I will be turning off the LED when the step value is less than 2048. So let's try to program that logic by configuring the microcontroller TM4C123 GH6PM in our KEIL Microvision IDE. So I'm just opening the KEIL Microvision. So I'm just going to build the project from the scratch by including all the CMSs and startup files. Click on the project, new Microvision project, and go to the respective folder, and here type in the project name and click on save. In this tab, select the device, that is nothing but TM4C123 GH6PM. Just type in the device name right over here in the search box so that this device will be listed. Double click on this and then click on OK. Here in this manage runtime environment tab, which is a very important tab, you just want to select the CMSS core which is much needed in our project, and then we just want to select the device startup code. So tick these two checkbox CMSS, we just want to select the score, and in this device tab just select the startup and then click on OK. You can see the project has been successfully created. Now right click on this source group and click on create new item to the source group. Here click on the C file, that is the .c file, and give the name as main.c, since we are creating the main.c file for our project. Now you can see the project has been created in KEIL Microvision IDE for the microcontroller TM4C123 GH6PM, and the main.c file has been created by us. Now for adding the header file, let me just right click on this and insert has include of TM4C123.h. And one more thing is that you can see here, this is the program that we wrote for blinking the onboard green LED in the lecture of interfacing LED with our TM4C123 microcontroller. So I am just going to copy this program and then I am going to alter this program for reading the ADC value. So let me just paste it right over here. I don't want this. So regarding the program, I have built this program step by step in that video. I hope you remember that video. So here I have just enabled the clock for Gpio port F, and here I have configured PF1 2 3 pins as digital pins, and here I have configured those 3 pins, that is PF1 2 3 as output pins. And here I am just turning on the PF3, that is the green LED pin available in my Tiva C series launchpad, waiting here for a particular rough delay. Here I am just turning off the same Gpio pin PF3. Again I am waiting here for a particular rough delay of same amount, and the blinking process goes on. So I don't want this blinking process here, so I'm just deleting this, but I want this configuration part, since I'm going to use this PF3 green LED for turning on the green LED if the ADC value goes beyond 2048, that is 50% of ADC value, and I will be turning off the same LED if the value comes below 2048. So let me just use this configuration of green LED. Let me just keep it right below, right over here, and these are all the configurations that we want to do for reading the ADC value from ADC channel, right? So let me just copy this and let me paste it right over here in the main, and let us do it step by step. So why I am doing this step by step is that you just want to get a clear understanding so that you will be able to interface any device to this microcontroller. So if I strictly show you the things that you require for interfacing a particular device to a microcontroller, you might feel a little bit difficult if you are doing any project on your own. So for that reason I am just doing this as step by step. So these are all the core steps that you want to follow for configuring the ADC module, and if you want any additional things you can try it on your own. So as per the configuration of Gpio as ADC channel, the first step that I want to do was I just want to enable the ADC clock using Rcgc ADC register. So let me just open the datasheet and search for Rcgc ADC. So surely it will be available under the system control tab, since it is a clock controlled register. Let me just go to the register map, and here it is. You can clearly see Rcgc ADC available in 352 page number. And this register particularly is having 2 bits, that is, this is the 32-bit wide register starting from 0 to 31, but all the bits from bit 2 to bit 31 are reserved. It is having only 2 read or write bits, and these 2 bits are R0 and R1, and R0 bit is meant for enabling the ADC 0 module, and R1 bit is meant for enabling the ADC 1 module. That is, if I write 1 to this R0, that is 0 bit of this register, ADC 0 will be enabled, and if I write 1 to this R1 bit of the register, ADC 1 will be enabled. So as I mentioned, I am just going to use the ADC 0 module of the microcontroller. So I just want to write 1 to the 0th bit of this register. So for the first step, we are just going to use the sysctl pointer. So for all the registers that is involving the system control tab, you just want to use this pointer sysctl, and I am just going to point to Rcgc ADC register, and I am going to enable or write 1 to the 0th bit of this register. So I hope you learned how you can set a particular bit in a register without disturbing the other bits, and how you can clear a particular bit in a register without disturbing the other bits. So this is the method for setting a particular bit in the register without disturbing the other bits. So we are just writing 1 to the R0 bit, that is 0th bit in this register, for enabling the ADC module 0 in run mode. And the next step that we are going to do is, we are just going to enable the clock to the appropriate Gpio module via Rcgc Gpio register. So Rcgc Gpio is the same register available right over here. You can clearly see this is the register which is useful for enabling the clock for a particular port. So let me just open that register. I hope you remember this register because we have been using this register for a while in almost every lecture. Let me just open this. This is the register, and here you can clearly see this is also a 32-bit register, but we are having only 6 bits starting from bit 0 to bit 5, and each bit is representing clock enabled bits of each port. Bit 0 is for Gpio A, bit 1 is for Gpio B, bit 2 is for Gpio C, bit 3 is for Gpio D, bit 4 is for Gpio E, and bit 5 is for Gpio F. So here in my program I have already turned on the clock for Gpio F since I have configured the PF3, that is the LED pin. But here what I want to do was, as I said, I am just going to use the PE3, that is analog input 0 of ADC 0 module for reading the ADC channel. I just want to enable the clock for the port E. So for enabling the clock for the port E, I just want to set the bit number 4 in that register. So let me just do that with the help of same pointer. I am just going to point to Rcgc Gpio register and I am going to set the bit number 4 for enabling the clock of Gpio port E. So this has been completed and this has been completed. Let me just erase each step one by one. And the third step that I want to do is, I just want to set the Gpio AFSCL bits for the ADC input pins. So since I am going to use a particular pin, that is PE3, as analog input pin, I just want to set the alternate function selection bit for this pin to be high. So that can be found in the register AFSCL. So let me just open that. I am going to the Gpio section of the microcontroller and I am moving to the register map. Here I can see, here is the AFSCL is in the 671 page. This is also a 32-bit register with values between 0 to 31, and it is having only the read or write bits to be 0 to 7, and each bit is representing a particular pin in a port. As we are having only 88 bits in each of the ports starting from Gpio A to Gpio F, each bit in this register is meant for configuring a particular pin in a particular port. If I am using the pointer Gpio E for pointing to the bit number 0 of this register, that means I am just configuring the PE0 pin as alternate function selection pin. Likewise, you can configure any pin, but in our case I just want this PE3 pin to be analog, so I will be setting the bit number 3 of this register to be high. So you can clearly see, if I write 1, the associate pin functions as a peripheral signal and it is controlled by alternate hardware function. And if you are not using any alternate hardware for the particular pin, and if you are going to use only the digital functions of the pin, you can make this bit to be 0. So I am just going to use the pointer Gpio E since I am going to configure the alternate function for port E, and I am going to point to AFSCL, and I am going to write 1 to the bit number 3. And obviously I just want to, since I have selected the alternate function selection pin for PE3, I just want to disable the digital functions for the particular pin. So I am just going to go to the DEN register, that is the digital enabled register, So let me just open the register DEN. So this is the digital enabled register. So this register is meant for enabling the digital functions for a particular pin. So similar to the AFSL, it is also having 7 bits active and it is a 32-bit wide register, and each bit is representing a particular pin in a port. And if I'm using the pointer Gpio, this 0 is meant for PE0, 1 is meant for PE1 and so on. And if I write 1 to a particular pin, the digital functions for the corresponding pin are enabled. And if I am clearing the bit, the digital functions for corresponding pin are disabled. Since I am going to use the PE3 as analog pin, I just need to make the PE3 pin, that is the third bit in this register, 0. I just want to clear that bit. So let me just use the same pointer Gpio for pointing to DEN register, and this time I am just going to clear the bit number 3. So this is the methodology that we have been using in a while for clearing a particular bit in a register without disturbing the other bits, right? So here I am successfully clearing the bit number 3 in DEN register. So fourth step is also complete. And the last and final step for configuration of Gpio as ADC channel is disable the analog isolation circuit for all ADC input pins that are to be used by writing a 1 to the appropriate bits of the Gpio AMSCL register. So let me just open the AMSCL register for enabling the analog function for the pin PE3. So it is also available in the Gpio segment. Let me just open the memory map, register map, and here it is. You can clearly see this is the register Gpio AM selection analog mode select register. It is available in 687, sorry. And you can clearly see this is also a 32-bit wide register, but it is having only active pins from 0 to 7. You cannot read or write the bits from 8 to 31, and each bit is representing a particular pin in a port. If you are using any other pointers, you will be pointing to a particular pin in the corresponding port. And writing 1 to any of the bits will configure the analog function of the pin enabled, or it will make the analog function of the pin enabled. So since I am going to use the PE3 as analog pin, I just want to point using the pointer Gpio to this register, and I want to set this bit number 3, so that I will be enabling the analog function for the PE3 pin to be enabled. So let me just do that with the same pointer Gpio. I am pointing to AM select, and I am going to set the bit number 3. And that's it. The configuration of Gpio's ADC channel is complete. We have successfully completed the configurations that needs to be done for a Gpio pin for acting it as a ADC channel. Next, we are just going to configure the sample sequencer of ADC channel for reading the ADC channel, or for configuring the ADC channel. Now let us try to follow these steps for configuring the sample sequencer. Before that, let us try to understand what is a sample sequencer. So while reading the analog signal from the ADC module of the microcontroller, you just want to use a sample sequencer in this series of microcontroller. So sample sequencers are nothing but a sequential process by which capturing happens in the ADC module. So there are 4 modes of sample sequencers available in the microcontroller: sample sequencer 0, sample sequencer 1, sample sequencer 2, and sample sequencer 3. You can use any one of these 4 sample sequences for reading the analog value. And if I am choosing the sample sequencer 0, the number of samples taken by the microcontroller ADC module will be 8, and the depth of FIFO, that is the first in first out FIFO, is 8. So 8 values will be stored in the FIFO, and if I am using the sample sequencer 1, the number of samples taken will be 4, and depth of the FIFO will be also 4. And for sample sequencer 2 also, number of samples will be 4 and depth of FIFO will be 4, and for sample sequencer 3 the number of samples taken will be 1 and the depth of FIFO will be 1. So I'm just going to use the sample sequencer 3. I don't want the samples to be fetched again and again at a time within a one read. So I'm just choosing the sample sequencer 3. So let us see the steps. Ensure the sample sequencer is disabled by clearing the corresponding ASEN bit in the ADC ACTSS register. So I just want to clear the corresponding sample sequencer 3 bit in the ADC ACTSS register. So let me just open that register for viewing in detail. ADC ACTSS. So here is the register ADC active sample sequencer register. So in this register we are having 4 bits available in the LSB part 0 to 3 and we are having 1 bit available in the 16th bit number. 16th bit number is the ADC busy bit. If this bit is 1, it seems to be ADC is busy, and if this bit is 0, the ADC is ideal. So you can only read from this bit and you cannot write to this busy bit. And regarding these 4 bits, which is useful for selecting the sample sequencer, that is, if I am writing 1 to ASEN3, that is bit number 3, the sample sequencer 3 is enabled, and ASEN2, that is second bit is meant for sample sequencer 2 enable, first bit is meant for sample sequencer 1 enable, and 0th bit is meant for sample sequencer 0 enabled. So for us, as I mentioned, I am just going to use the sample sequencer 3. So I am just going to write 1 to 3rd bit of this register. So regarding the pointer that we are going to use here is, as I mentioned, we are just going to use the ADC 0 available in the microcontroller. So the pointer is ADC 0. ADC 0, and I'm just going to point to ACTSS, and I'm going to write 1 to the 3rd bit for enabling the sample sequencer 3, using which we are just going to read from the ADC channel. And the second step is configure the trigger event for the sample sequencer in the ADC mux register. Let me open the ADC emux register. Here is the ADC emux register, that is the event multiplexer select register. And this register is also a 32-bit wide register, but it is having only 16 bits starting from 0 to 15 in the LSB part. And in this register, these 16 bits are subdivided into 4 different parts. That is, bit number 0 to 3 is meant for EM0, and bit number 4 to 7 is meant for EM1, bit number 8 to 11 is meant for EM2, and bit number 12 to 15 is meant for EM3. Let me just see what is this EM0 to 3. So the bit numbers from 12 to 15 is meant for sample sequencer 3 trigger select, and this field selects the trigger source for the sample sequencer 3. And bit numbers from 8 to 11 is meant for sample sequencer 2 trigger select, and it will be selecting the trigger source for sample sequencer 2. And similarly, 4 to 7 is meant for sample sequencer 1, and 0 to 3 is meant for sample sequencer 0. And as we are using sample sequencer 3, we will be configuring the bits from 12 to 15, that is these 4 bits, and we will be leaving all the other bits. So what we want to write here is, we just want to leave the triggering process ideal by writing 0x0000 to all these 4 bits available from bit number 12 to 15, because if it is 0x00, that means the processor will be triggering the ADC event. We want that also, that is, the trigger is initiated by setting the SSN bit in the PSSI register. So for reading a particular ADC value or for performing an analog to digital conversion, I just want to set the particular SSN bit in the ADC PSSI register. So once I do that, the conversion will be happening if I am writing 0000 to bit numbers from 12 to 15. So for that purpose, I just want to write 4 zeros to the bit numbers from 12 to 15 in this register, and regarding all the other bits, I will be making it 0xf, that is always. So I don't want any other bits to be changing in this register, but I want to write 0x0 to this bits from 12 to 15 in this register. For initiating the trigger by you setting the SSN bit in the ADC PSSI register. So for that, what I can write is ADC 0 Emux ampersand is equal to negation of 0xf000. So f means 1111, 0 means 000, 0 means 000. So by writing this value of 0xf000, we are just clearing the bits from 12 to 15 in this register, and we are setting all the other bits from 0 to 11 in this register. So you can write this as a whole value, or you can use this methodology of this one ampersand is equal to negation of each individual bits for clearing the register bits. But I am just doing this as a whole. And the next step that we are going to do is we just want to, when using PWM generator as a trigger source, use the ADC trigger source select ADC TSSCL register to specify in which PWM module the generator is located. The default register reset select PWM module 0 for all registers, all generators. So we are not using any PWM generators for triggering the ADC value or the conversion. So I am just deleting this point. I don't want to do this. And as the next step, we just want to, for each sample in the sample sequence, configure the corresponding input source in the ADC SS mux n register. So let me just open the ADC SS mux register. Here is the ADC SS mux register available in the page number of 851. Here we are having 32 bits available in this register, which we can read and write. And it is also divided into 8 different parts for mux 0 to mux 7, and each mux is having 4 bits. And you can clearly see the bits from 28 to 31 is meant for 8th sample input select, and bits from 24 to 27 is for 7th sample, 20 to 23 is for 6th sample, 16 to 19 is for 4th sample, 12 to 15 is for 3rd sample, 8 to 11 is for 2nd sample, 4 to 7 is for 1st sample, and 0 to 3 is for 0th sample. So for enabling the input, I just want to write 0 to the corresponding mux 4 bits. That is, if I want mux 0 to be enabled, that is input 0, I just want to write 00000 to all these 4 bits from 0 to 3. In the similar manner, I just want to perform for all the mux from mux 0 to mux 7. But here you can clearly see this is meant for sample sequence input multiplexer select 0. So it is for sample sequencer 0. It is clearly mentioned, but we have configured the sample sequencer 3. So here you must remember that I have configured the sample sequencer 3 for reading the ADC value. So let me just find the ADC mux 3 register, and here is the mux 1, mux 2, and finally here is the ADC SS mux 3 register. So this one is meant for sample sequencer 3, and here I am having only one channel available, mux 0, which is the first channel. So I just want to write 0 to all these bits from 0 to 3. So let me just write ADC 0, SS mux 3 is equal to 0x0, which will write 0 to all the LSB4 bits. The next step that we want to configure is, and the next step that we want to follow for configuration of sample sequencer for ADC channel is, for each sample in the sample sequencer, configure the sample control bits in the corresponding nibble of ADC SSCTLN register. When programming the last nibble, ensure that end bit is set. So I just want to go to ADC SSCTLN register. So ADC. So here you can see, here is the ADC SSCTL register, which is nothing but the ADC sample sequence control 1 register, which is meant for sample sequencer 1, sample sequencer control 2 register, which is meant for sample sequencer 2, and similarly we just want to configure the sample sequencer 3. So here is the ADC SSCTL3. So this is the register that we want to configure, and in this register we just want to write 1 to this IE0 bit, which is useful for enabling the raw interrupt signal once the ADC conversion is complete. So using this signal only, we will be able to find that the ADC conversion is complete, so that we can read the ADC value. And then we just want to set 1 to the end 0 bit, which is useful for starting the single sample sequence. So this register is also 32-bit register, but it is having only 4 bits at the end. So in this 4 bits, in these 4 bits, we will be enabling only these 2 bits, bit number 1 and 2. This end 0 is useful for starting or initiating the sample sequencer, and this IE0 is meant for indicating us with an interrupt that the ADC conversion is complete. So we are just enabling the raw interrupt by writing 1 to this second bit. So I am just going to go to the SSCTL3 register, and I am going to write 1 to bit number 1 and 2, that is end 0 and IE0 has been enabled. And as the final step, if the interrupts are to be used, to set the corresponding mask interrupts. I am not using interrupts, I am just going to fetch the ADC value using polling method. And finally, I just want to enable the sample sequencer logic by setting the corresponding ASEN N bit in the ADC ACTSS register. That is, sorry, I just made a mistake. That is, I just want to clear this bit as the first step, and I want to set the same ASEN bit right over here. So before configuring all these things, I just want to clear this ASEN3 bit, and after the configuration, I just want to enable this bit. And that's all about the configuration of sample sequencer of ADC channel. And below this, I have configured PF3 as output, and I have enabled the clock for the PF3 pin, which is connected to green LED in the TIVA C series launchpad development board. So now that the configuration is complete, now let us try to write some programming logic for reading the ADC value from channel 0, that is PE3, to which the variable resistor is connected, and then we will turn on the LED if the value goes beyond 2048, and we will turn off the green LED connected to PF3 when the value drops below the 2048. And also we will be visualizing the step value in the debugger available in the KEIL Resolution IDE. So for reading the step value, the first and foremost step that we want to do is, we just want to start the conversion by setting SSN bit in the PSSI register. So let me just open the PSSI register. Here is the PSSI ADC processor sample sequence initiate register. So this register is useful for initiating all the sample sequences for starting the ADC conversion. So here we are having 32 bits available in the register, but we are just going to use only these 4 bits available from bit number 0 to 3. And these 4 bits, bit number 0 is meant for SS0, sample sequence 0, 1 is meant for 1, 2 is meant for 2, and 3 is meant for sample sequence 3. And we are using sample sequence 3, so I just want to write 1 to this third bit of this register for begin sampling on sample sequence 3. So I'm just going to, coming inside the while of 1, which is the infinite loop of the program, I'm just going to use the pointer ADC0 for pointing to PSSI register, and I'm going to write 1 to bit number 3 for beginning the sampling process. That is nothing but the analog to digital conversion process. And after that, I just want to check for the interrupt to detect conversion complete in RIS register. So there is a register called RIS. We have enabled the IE0 bit in this line, right, for indicating that the conversion is complete with the help of raw interrupt. So we can detect the flag for that interrupt in a register called RIS. So here is the ADC RIS, that is the raw interrupt status register. So in this register, this is also 32-bit register, and we are having main bits 0 to 3 available right over here. And each bits from bit 0 to bit 3 is meant for separate sample sequencer. Here also you can clearly see the third bit is INR3, which is meant for sample sequencer 3. And if this bit is 1, a sample has completed conversion and the respective ADC SSCTL3 IEN bit is set, enabling a raw interrupt. That is, we cannot raise this flag, but this flag will be raised automatically when the conversion is complete and the data is readily available in the FIFO register. And this bit is cleared by writing 1 to the IN3 bit in the ADC ISC register. So let me just check for this bit to be 1. So that can be done with the while loop right over here, that is ADC RIS ampersand of 0x8, waiting here. So until I am reading the value 0x0 with the process of ADC0 of RES ampersand of 0x8, I will be waiting here with this while loop, and if it is high, this loop will be exited because this condition is failed, since I have terminated this loop right over here. So for checking for any flag in the register, you can use this methodology, or even you can use this term 1 left shift of 3 right over here. Both are same. And once the flag is high, that is the conversion is complete, the program will be coming right over here, and here I will be reading the data available in FIFO register, that is respective FIFO register. So FIFO is nothing but the register. Right over here you can see ADC sample sequence result FIFO 0, result FIFO 1, 2 and 3. So this is the register in which the ADC value will be loaded, that is the 12-bit ADC value will be loaded. Since I am using the sample sequencer 3, I am just going to read from the ADC sample sequence result FIFO 3. So let me just do that. I'm just using a variable named ADC value. I just want to declare this variable right over here, uint16 underscore t ADC value. So obviously this ADC value will be holding values between 0 to 4095, since it is a 12-bit ADC. So that is why I have declared this variable as uint16, which will be holding the values between 0 to 2 to the power 16 65535. ADC value is equal to ADC 0 SS FIFO 3. And after reading this, as mentioned in the RIS register, I just want to clear the interrupt flag for this interrupt rise. So I'm just going to ISC register right over here. This is the interrupt status unclear register. Here also we will be having the same 4 bits bit number 0 to 3, IN0, IN1, IN2, IN3, and each is mentioning for a separate sample sequence here. So I just want to write 1 to the bit number 3 for the sample sequencer 3. So let me just do that. Here I will be using the ADC 0 pointer for pointing to ISC, and I am going to set bit number 3. And here what I will do is I will be just checking for the ADC value. If it is greater than 2048, Gpio F data R is equal to 1 left set of 3. So I am just turning on the green LED if the ADC value goes beyond 2048, and if it is not, if this condition fails, I will be turning off the same PF3 bit. So here I am just continuously reading the ADC value with the help of a variable ADC underscore value, and if the ADC underscore value goes beyond 2048, the LED will be turned on, and if it is not, it will be turned off. So this is the programming logic that I have written. Since all these lines are written inside the while of 1, this happens every time until the microcontroller is stopped. So the ADC value will be fetched, and this checking process happens each and every time until the microcontroller is stopped. So let me just build this project. You can see the build is successful with 0 errors and 0 warnings. And now let us try to visualize the output in the hardware after building a circuit in the breadboard. Now you can see this is the TIVA C series launchpad development board, and this is the 10 kilo ohms variable resistor or the potentiometer, which we are going to use for fetching the analog DC voltage signal to the analog pin of this microcontroller. So this is the 10 kilo ohms resistor which we are going to use as a analog source for the analog pin of this microcontroller. So let's look at the connection between this potentiometer and this development board. So usually this potentiometer is having 3 terminals, namely one on the left, middle and on the right. So what I will do is I will connect this left terminal to the ground of this development board, center terminal to the analog pin PE3 of the microcontroller, and rightmost terminal I will be connecting it to power source, that is the 3.3 voltage pin of the development board. So that's all about the connection. I am just going to make the connection. I am connecting the left side terminal of this potentiometer to the ground of this development board. You can see I have connected it to the ground of the development board, TIVA C series launchpad. And regarding the center pin, I am just going to connect this center pin to the analog channel PE3 of this development board. So here is the PE3, you can clearly see I have connected the pin to the PE3. And regarding the rightmost terminal, I am just going to connect this rightmost terminal of this variable resistor to the 3.3 volt signal. So here is the 3.3 volt signal. I am just going to connect it right over here. You can see I have connected this pin to the 3.3 volt signal. Yellow pin has been connected to ground, and the center terminal has been connected to PE3. And that's all about the connections that we want to do. Let's take a look at the output in the hardware. Now I am just going to compile this sketch, that is the program. You can see I am getting 0 errors and 0 warnings. Now I have already connected my TIVA C series launchpad development board to my PC, so I am just dumping the program to the microcontroller with the help of this download button. You can see the flash has been loaded to my microcontroller. Now for viewing the step value of the ADC, I am just going to enter into the debug mode of this KEIL Microvision IDE. you can see the IDE has shifted the view from editor view to debug view. Now you can see this is the variable, right? This is the variable ADC underscore value is the variable which is holding the 12-bit step value from the ADC. So I am just going to add this, double click on this, right click and then hover over this add ADC value to watch 1. So I am just adding this variable to watch window for viewing the value that is holded in that variable. So you can see ADC value has been added to the watch window of this debug mode. Now for running the microcontroller, just click on this run button. You can see the ADC is having the minimum step value 0. And now when I slightly turn the potentiometer knob, you can see the value increases as per the rotation of the knob of the potentiometer. You can see the LED has been turned on. As per our logic, we have written that if the ADC value goes beyond 2048, that is the 50% value of the step value, we are just turning on the LED, right? You can see the green LED has been turned on as per our logic, and further when I rotate the knob, you can see the value increases, and when I reach the other extreme end, I am having the maximum step value to be 4095. So this is the logic, right? We are successfully reading the DC voltage signal with the help of ADC module through the pin PE3 of this development board of the microcontroller TM4C123. So our ADC module is working fine in this microcontroller. We have successfully configured the ADC module for fetching the voltage signal as a DC step value. See you in the next video. Thanks for watching. So this is the output that I got in my hardware. When the step value is greater than 2048, the LED will be turned on. When it is less than 2048, LED will be turned off. Greater, less, greater, less, greater, less, greater than 2048, less than 2048, greater than 2048, less than 2048. So now I hope I covered all the points available in this agenda. You learned what is a variable resistor, what are all the applications of variable resistors and functionality of variable resistor, and also you learned how you can configure the ADC module available in the TM4C123 microcontroller, and we learned how we can interface the variable resistor to ADC module available in the same microcontroller, and finally we just built the circuit and visualized the output in the hardware. And finally, I hope you learned something new in this video. See you in the next video. Thanks for watching.